We've already used some static routes so far, but I've promised I'd explain them further, so here I am. First, some basics. Static routing means there is someone, usually a network admin, who must manually enter all networks in a domain into the routing tables. When a change occurs within that domain, the administrator must manually update the tables. Dynamic routing, however, is what we'd use to describe routing protocols. In that case, a protocol on a router communicates to that same protocol on a neighboring and other adjacent routers in that domain. When something changes there, the routers using that protocol inform each other of the change and, as a result, update their tables automatically. This stuff is best explained in an example, so let's take this one. Here we have two routers. Let's call them router on the left and router on the right. And we have three networks. Networks 1.0 and 3.0 are obviously local area networks. And then this 2.0 network is a WAN network, a wide area network. We can see the two routers' routing tables here, and let's analyze them. In both routing tables, we can see all three networks listed. And for the router on the left, we have networks 1.0 and 2.0 are directly connected, and we can see through which interfaces. The metric here is actually the number of hops. So if a network is directly connected to a router, there are no additional devices a packet must go through from this router to reach these two networks. However, that is not the case for this network right here. So from the perspective of this router on the left, network 3.0 is a remote network. So in order for a packet to get from this router to this network, it has to go through router on the right, which means there is one hop to jump. We can say it like that. Okay, for the router on the right, it's a very similar situation. So networks 2 and 3 are directly connected. Here's network 2 and here's network 3. And then network 1 is a remote network, and there is one layer 3 device or one router that we must jump, so to say, in order to get from this router to that network. In short, what a router does when it receives a packet is it looks at that packet's destination address, and let's take, for example, that this PC sends something to this PC over here. So we have a packet going from 1.1 or 1.1, however you want to say it, to this PC with IP address 3.1. That packet will get into this router through E0 interface. The router will look at the destination IP address, it will look at the mask, and then it will say, okay, so I need to send this packet to this 3.0 network. It's in my routing table, here it is. The interface that I need to use here to send this packet out is interface serial 0, and here is the metric. Now, since this is the only route I have for that network, the metric doesn't really matter. It would matter if I had another route to that network, and then I could compare those two routes using their metrics. Okay, this is all very nice, but these two routers already had complete routing tables. You might wonder, how do you actually add routes into a routing table? Because at the very beginning, when we talk about static routing, these two tables would be empty. We would have to manually add routes into routing tables. Well, in Cisco devices, you add a route by using this command. You use IP routes, and then net2 is the remote network that you want to reach, and so you're creating this very route. And then you need the mask of that remote network. And then in the end, you specify how to get there. Remember, all that a router cares about is what is the next hop for that packet. As soon as it receives a packet, it starts looking for the destination network in its routing table. But in the routing table, there's no information on the entire topology or something greater than that. When you use routing protocols, each router is aware of the topology, but in the routing table itself, it's just the exit interface or the next hop address. We actually have two options here. Tell the router which interface to forward the packet to or which neighbor to send it to. There is a difference between those, and I'll explain it later. In case you make a mistake, you delete a route by just adding no in front of it, pretty much as all other commands in Cisco. So let's look at another example. This time we have 3 routers and 2 networks. And this time our goal is to create the necessary routes ourselves. So our goal here is to have all of these routers be able to communicate to each other. At this point, without any routes, R1 and R2 can communicate because they are directly connected, and then R2 and R3 can communicate because they are directly connected, but R1 and R3 will not be able to communicate. What did I do? Okay. Let's look at router 2 first. So we have 2 networks in this scenario here, and both of those networks are directly connected to router 2, so we don't need to add anything on router 2. We do need to tell router 1 how to get to this network 2000. And we do need to tell router 3 how to get to this network 1000. Let's start from router 1. So on router 1, we would say IP route and then define the remote network, which is 2000. And then we would have to specify the mask of that network, which is 255.255.255.252. And then we would need to tell router 1 where to send that packet. And that would obviously be, if we are defining the next hop IP address, that will be 1002. So this is the full route. And then the route we need to add on router 3 would be IP route 1000, because that is the remote network we want to reach. And then the mask is the same. And then the next hop address is 2001, because if we want to reach 1000 from router 3, we need to send the packets through router 2, and this is the full command. In order to list all of your routes, you can use this command, show IP route. It will show you the entire routing table on your router. You may have noticed that static routing configuration gets exponentially complicated as you add routers or networks. Default routes are useful when you have a network, and that type of network is called a stub. And that is a network or a router which, if you wanted to add routes for all of the remote networks, all of those routes would have the same exit interface or the same next hop. So you can just use all zeros to say for all destination networks with any subnet mask, send this way. Let's use an example again, shall we? First thing we need to do here is list all of the static routes we'd need for all of the hosts in this network to be able to communicate to each other. Let's start from router 1. And let me clear up one thing here. I remember some of my students used to not realize this right away. So if we look at router 1, for example, and we have this network 192.168.1 connected to it, say PCA wants to send something to PCD. That packet would get to router 1. Router 1 would look into its routing table, and if we haven't configured anything yet, it would drop the packet because it has no instructions on what to do with it. The conclusion there is that router 1 needs a route to 192.168.3. That is the network in which PCD is sitting in. Okay, so let's start again. PCA sends a packet. Router 1 receives it. It sees it's destined to 192.168.3. It finds a route. The route says sent it to router 2. So router 1 sends the packet through its serial interface. Router 2 then receives the packet, opens the third layer, sees destination IP is 192.168.3, looks at its routing table, but there's no route for that network, and then router 2 drops the packet. Moral of the story, all routers must know routes to all networks. It is not enough that only the first hop router has the right route to the destination network. All of the routers on that route must know where the destination network is. Oops, I just messed that up. Okay. Let me finish this example. So we add the route to 192.168.3 to router 2. So router 2, when it receives the packet, it forwards it to router 3, and then router 3 doesn't need a route to 192.168.3 as that network is already directly connected to router 3, which means it is by default already in the routing table. Okay, so let's go back to the challenge. List all of the static routes. Starting from router 1. Router 1 would need a route to 2000 network, 192.168.20, and 192.168.30. Router 3 is symmetric to router 1. It needs routes to 1000, 192.168.2, and 192.168.1. Router 2 has 3 networks directly connected to it, this one, and this one, so it will only need 2 routes, the route to 192.168.1 and 192.168.3. In total, that is 8 static routes. Next task, which of the routers can use the default route? So for router 1, we said it needs 3 routes. If we list those 3 routes, all of them will have the same exit interface or next hop. So we can use the default route there. Instead of 3, we will use 1. Same goes for router 3. All the networks router 3 needs to reach or that are not directly connected to it are behind this serial 001 interface. So we can use a default route there as well. But what about router 2, you might ask? Well, in this entire topology, only 2 networks are not directly connected to router 2. Let's take a look at those 2 networks. The first one, 192.168.1, is reachable from the perspective of router 2 through its serial 000 interface. So this interface on the left. The other network, 192.168.3, is reachable through its serial 001 interface. Obviously, this router will be sending traffic through more than one interface, and therefore it's not a stub network, and therefore a default route is not suitable for this situation. By the way, there's a packet tracer file from this presentation for you in the resources. All is configured and the only thing missing are the routes. We will use a more complex topology for the exercise, but if you're in the mood, feel free to practice with this one as well. I want to show you one more thing before we head into our exercise. The administrative distance, or short AD. First of all, you should know that the lower AD is better than a higher AD, the lowest value being 0 and the highest 255. Now, I kept repeating that there's a difference between listing an outgoing interface versus the next hop in static routes, and this is pretty much it. AD is better for an exit interface. For the exit interface, it's 0, and for the next hop, it's 1. But you can manually change that, like in this example here. You can use the command we've already learned for adding a static route, and then just add the AD value at the end. Hopefully it's obvious why you'd want to use this, but if not, we'll do it in our upcoming exercise. In short, when you have two redundant routes and you want to influence the routing so that your router uses one route over the other, you can do it like this. By the way, AD value is not tied only to static routing. It is very well used in dynamic routing as well. You can see the default values for the most used routing protocols at the bottom of the slide. The best value holder is EIGRP because, you know, it's Cisco. No, just kidding. Sorry, Cisco. And after EIGRP comes OSPF, and then the worst is RIP. But we will discuss this in the future lessons as well, so let's not waste time now and head straight into the exercise.